Imagine designing a machine to mimic the moral judgment of humans. In principle, you may want a machine that is better than humans at making moral judgments. But in practice, that goal may be too far-fetched. So instead, you may want to first make a machine that simply mimics the moral judgment of humans. The goal of this chapter is to explore the very basics of that machine. To achieve that goal, we will use simple statistical tools that prioritize explicability over accuracy. These tools will help us zoom out of individual scenarios by providing descriptions that are less nuanced but more generalizable. They will also inform us about the impact of different inputs into moral judgments. Our exploration will build on the ideas of a moral function. This is a mathematical object predicting how people will judge the outcome of a moral scenario based on inputs, such as who is performing the action or its level of perceived harm. One input that is of particular interest for us is whether the agent performing the action in a scenario is a human or a machine. Throughout the course, we have seen that people judge human and machine actions differently. This is consistent with the social psychology literature telling us that people judge and punish more severely members of outgroups, in our case machines, than members of the in-group, in our case humans. By using moral functions, we can formalize those differences by exploring how they relate to the characteristics of a scenario. Our approach will rely on many simplifying assumptions which we introduce in an effort to prioritize clarity. To make that explicit, we will mention the problems caused by these simplifying assumptions when we introduce them. To begin, we introduce the moral space, a quantitative representation of moral judgment. This representation, which we use to abstract away from the details of each scenario, is inspired by Jonathan Haidt's moral foundation theory and is based on three factors: harm, intention, and wrongness. While in principle we could include many inputs such as whether the dilemma involves an uncertain outcome or represents a violation of a moral dimension other than harm, we focus for simplicity only on 5 variables: the perceived level of harm, intention, and wrongness, and also whether the action in a scenario was performed by a human or a machine. Later, we also explore how the characteristics of the people judging the scenario affects moral judgments. In the moral space, each scenario is represented by 2 dots connected by a line. The red dot shows the judgment of the machine action, while the blue dot shows the judgment of the same action when conducted by a human. The dots exist in a 3-dimensional space defined by wrongness on the vertical axis and harm and intention on the horizontal plane. We use a diverging scale for wrongness, meaning that wrongness values range from extremely right to extremely wrong, with the neutral value around 0.5 being neither right nor wrong. For harm and intention, we use a sequential scale, that is, intention ranges from not intentional at all to extremely intentional, and similarly, harm ranges from not harmful at all to extremely harmful. We can use this representation to summarize the patterns found across all the scenarios that include questions on perceived wrongness, harm, and intention. This excludes the privacy and labor displacement scenarios which did not include these questions. This 3D figure shows a summary of our experimental results. The first finding, which is interesting but kind of obvious, is that moral judgments do not populate the whole space. They fall within a plane that extends from the upper left corner with high levels of harm, wrongness, and intention to the right side of the cube, which shows the scenarios with low levels of wrongness and harm. This is because some corners are forbidden. For instance, scenarios with no intention or harm cannot be high in wrongness. Now let's zoom into the harm-intention plane. Here we see that machine actions are seen as less intentional than human actions when the level of human intention is relatively high. This is true for most cases in our sample. However, we find 6 scenarios in which the actions of machines are seen as more intentional than those of people. These 6 cases are all at relatively low levels of intention and include the excavator scenario, the wrong national anthem scenario, the school demolition scenario, and the 4-car accidents. The harm intention plane reveals 2 things. The first, which is obvious, is that in most cases people appear to assign more intention to human actions than machine actions. The second, which is more surprising, is that people may excuse human actions more than machine actions in accidental scenarios. For instance, when a car accident is caused by either a falling tree or a person jumping in front of a car, people assign more intention to a machine driver than to a human. As discussed in previous chapters, this suggests that people perceive an accident more like an error when the actor is a machine, but as a misfortune when the actor is a human. Hence, in this type of scenarios, they forgive or excuse humans more than machines. Next, let's look at the wrongness intention plane. We also see a triangular pattern because intention modulates the level of perceived wrongness. Unintentional actions cluster close to the neutral value of 0.5, meaning neither wrong nor right. But actions perceived as intentional can score very high, extremely wrong, or very low, extremely right. This is consistent with an extensive body of literature in moral psychology showing that intentional actions are judged worse than accidents, even when the accidents have more serious consequences. But the wrongness intention plane also reveals some interesting pattern. For low levels of intention, we see a clear upward slope, meaning that machine actions are perceived as both worse and more intentional than those of humans. This group contains the 4-car accident scenarios. At an intermediate level of intention, we find actions that are perceived as less intentional for machines, but also worse. These examples include those of unlucky decisions under uncertainty, like the tsunami scenario. But at high levels of intention, differences in the intention attributed to humans and machines correlate with differences in the level of perceived wrongness. For high wrongness, human actions are judged as more intentional and more morally extreme. This group consists of cases involving discriminatory treatment in school admissions and human resources. For low wrongness, machine actions are seen as less intentional but are still judged worse than the equivalent actions performed by a human. This group includes cases that involve correcting an unfair treatment, such as in school admissions and human resources. In other words, because human actions are seen as more intentional, humans are perceived as more morally right than machines in scenarios with strong positive outcomes, and as more morally wrong than machines in scenarios with strong negative outcomes. Finally, we look at the harm wrongness plane. Unsurprisingly, we see a strong positive correlation between perceived harm and perceived wrongness. Yet we also observe regions characterized by different regimes. For positive outcomes, we find no big difference between the harm attributed to a machine or a human action. But we do find that machine actions are judged worse. At intermediate levels of harm and wrongness, we find actions that are perceived as more harmful and worse when performed by machines than humans. In fact, the evaluation of these scenarios is so extreme that humans are, on average, perceived to be morally right, in situations in which machines are perceived on average as morally wrong. In this region, machines are also perceived as more harmful. This cluster is populated by accidental scenarios, including the car scenarios, the interest rate scenario found in the appendix, and the unlucky outcome of the tsunami scenario. In these uncertain cases, people are less forgiving of machines and judge actions as more harmful and morally worse when they are performed by machines. Finally, for scenarios rated high on harm and wrongness, we find 2 groups. The first one involves cases of algorithmic bias related to fairness. Here, human actions are seen as both slightly more harmful and also worse than the equivalent actions performed by a machine. The second group, which exhibits the opposite trend, consists of 2 cases of accidental manslaughter, such as the terrorist scenario and the ambush scenario found in the appendix. Here, machine actions are seen as more morally wrong than those of humans, suggesting once again that the bias against machines is modulated by a scenario's moral dimensions. The moral space tells us that the way in which people judge the actions of machines compared to those of humans varies across the scenarios. When intention and harm are low, people appear to be less forgiving of machines, evaluating their actions as worse. When intention and harm are high, people tend to judge human actions as worse than the equivalent machine actions. Of course, the results presented here should be taken with a grain of salt. Despite the apparent clarity of these trends, the moral space should include factors beyond a scenario's perceived level of harm and intention. For instance, in scenarios involving a dimension of fairness, such as the algorithmic bias scenario, humans are judged more harshly than machines when they do wrong and more positively when they do right. But in scenarios involving physical harm, such as the car accident, tsunami, and manslaughter scenarios, the opposite is true and machines are judged more harshly. But can we formally model these patterns? In the next section, we model these moral surfaces mathematically to understand more systematically when people have biases for or against machines.